Welcome back to London Learning Lean. Next week, it's Nico who's going to tell us about, I can't say your lot, is it Cavalieri?
Cavalieri,
yeah. Nico Cavalieri is going to tell us about topological vector bundles. But this week, we're very pleased to have Kenny Lau, who's going to tell us about his MSc thesis on tilting perfectoid fields.
Thank you.
Yeah, go on, sorry. I was going to say, did I record? Yes, I did.
Yeah, I'm Kenny Lau. I'm now currently studying PhD in University of Cambridge, and this is my master's thesis when I was in Imperial College. So this is about tilting perfectoid fields, and this is the big thing that that won Peter Schulze his Fields Medal. So let's see what this is all about. So there's this weight monotony conjecture, which is a big thing. So what does it say? So firstly, we need to have we're working over a local field K of mixed characteristic 0p, and the residual field, we will call it kappa. So this will, for example, like you can just pretend K is QP, like the p-adic numbers, because that's the like canonical example of a local field. And Kevin might have a few words to say about canonical. Our residual field in this case will be the field with p elements, which is Fp, and it is finite. So we have the Frobenius map in its algebraic closure, which is like raising by power p, or some people want the inverse of that Frobenius map. So which one they want will depend on the context. One is called the arithmetical Frobenius map, and then one is called the geometrical Frobenius or something like that. And then the point is that once we have this Frobenius map, we can lift this Frobenius map to a map on the algebraic closure of K. So we have this phi, which is a map on K bar, and then now we have a X, which is a proper smooth variety over K. And if you don't know what this means, you can just pretend that this means pretend that this is like some hypersurface in like PNK, which like the projective space of K. So you can just pretend X is like a subset of PNK defined by like an irreducible equation, polynomial equation. And then now we want to analyze the eigenvalues of this phi on this cohomology group, which is like you take base change to the algebraic closure of X, and then you take the coefficients to the QL bar. So I assume this is a tau cohomology. Someone will correct me otherwise, but you know, so this we just taking like cohomology, and then this phi will act on this thing because it acts on K bar. So we want to analyze the eigenvalues, and then this should be a finite dimensional vector space over like QL bar, and then so it has like eigenvalues, and then the conjecture is like these eigenvalues will be like a fixed amount, which is determined by K and some other indices. So the status of this conjecture is like, so firstly, like in the beginning, in like 1980, Deligne proved this conjecture for curves over characteristic P. So this K here is replaced with just a field of characteristic P, maybe more assumptions, and then X has to be a curve, so it can only be one dimension. Some other assumptions may exist, and then Terasoma and Ito in like near the 2000s, they proved independently. This is like independently, but they proved this conjecture for general varieties over characteristic P. So it doesn't need to be dimension 1 anymore. So it can be any dimension, which is like, so this is a generalization of the previous result. And then Rappaport and Zink, in just 2 years after they proved this result, proved it for mixed characteristic, but the dimension has to be at most 2, so like a curve or a surface, and it needs to have what is called a semi-stable reduction. So there's like a condition for what happens when you reduce it like to the characteristic P, because so mixed characteristics. So we have this, we can keep this K here, and then when we change our variety to base kappa, then there needs to be some condition called the semi-stable reduction. So there's a sort of generalization of this, but in other directions. So like this is like generalizing the field, and then this is generalizing dimension. So, and then what happens after that is that de Jong, in like 1990s, he managed to prove this without assuming the semi-stable reduction by basically reducing to this previous case. But the dimension still needs to be like almost 2. And then finally, in this paper of Schulze, he proved this theorem when x. So it's still not the complete general theorem, but there's a more general assumption in x, which is that x needs to only be geometrically connected and set theoretic complete intersection in a toric variety. And you can just trust me that this is more general than this. So like, yeah. So for example, any hyperplane or like hypersurface will work in like Pn. So there's a considerable amount of generalization. And then now, so the question is, how did he do that? Right? The question is, how did Schulze prove this? And then the general idea is that he borrowed the result for characteristic P. So basically what he did is that he built a bridge between things of mixed characteristic and things of characteristic P. And you recall that the status for characteristic P is like much more understood because it has been proved in general for any variety, like it's smooth and maybe connected and proper over characteristic P. So if we have sort of this bridge between these two things, then somehow we can borrow these results from characteristic P to our mixed characteristic case. And then the question is, what does things mean? So things can be like rings, fields, varieties, sheaves, and sites. So like we need to consider a lot of things. Like once we have the varieties, then we have like functions over it, which will be a ring, and then modules over like modules defined on the varieties will be like sheaves, and then sites will be like more general stuff. And then what does a bridge mean? Well, bridge is like a category theory thing, because these things they like form each of them they form like their own separate category. So this bridge thing is maybe like functor, or maybe you can maybe even the equivalence of categories. So you want to go both ways. And this and here what Schulze builds like this bridge, he calls it tilting. So like you can have like a field, like a local field of like mixed characteristic, and then maybe with more assumptions, and then you can tilt it to get a similar looking field, but it has characteristic P. So this is what this whole thing is about. And in my paper, in my project, I sort of briefly explain the main ideas behind tilting, which will involve things like almost mathematics, which is like invented by some other authors. And then they also need like the cotangent complex, which is invented by Luc Illuzy, and then some other more advanced, complicated stuff that somehow Schulze united all together, and then he put these ideas together and he managed to build this bridge called tilting, and then he was able to prove that this is an equivalence of categories with like fields and some other stuff. So let's look at a basic example of tilting to sort of get a general idea of what this thing does. So as I said, when I say mixed characteristic, then the canonical example is QP, which is the completion of Q under the p-adic norm. And the important thing about this p-adic norm is that p to the n is considered to be small. So for example, 1 plus p to the n will be very close to 1. Even this sequence will even converge to 1 under this norm. And then once we complete it, then the whole point behind completion is that we have more analytical tools to study things, even though this is like very different from R, like the real numbers, which is a different completion of Q. Like in the topology is very different, but somehow it's like more useful in some regards. So, and then we also want to consider like extensions of QP, which are like well understood by the local class field theories, and in particular so to tie to Lean, this QP is already in Lean, although I didn't write this. We have this p-adic thing in this number theory /p-adic p-adic numbers dot Lean. We have this p-adic numbers defined to be just p-adic, and then it's defined to be the completion of the Q under the p-adic norm specified by p. So so obviously it takes p as a parameter because QP depends on p, and then we also have this notation of Q underscore and then square bracket and p and inside mathlib. So this is inside mathlib already. Now this with QP we cannot tilt QP just yet because it is not within like it's like not good enough. So what do is we adjoin p to the nth roots of p to obtain this extension, which is called totally ramified over QP, whatever that means. So this is some sort of ramification is like some sort of condition on the new norm. So all these local fields and like p-adic field, characteristic p fields, they all come with a norm in our case because we like analysis. And then this ramification is saying that the norm sort of the possible values of the norm sort of gets like denser and denser and denser, and then this so once we adjoin p to the nth roots of p, we will have this infinite extension of QP. And this is still not enough because somehow it is not complete analytically. So we need to complete it again. We get this field, we call it K. So it's just the completion of this thing. And then now this field is good enough and we can tilt this field. So what does that mean? Before that, these normed fields have rings of integer. So this is like, so for example, for QP, the ring of integers will be ZP, and it is always defined to be the elements with norm at most 1. So because of this, so if you this doesn't work if you consider like the real numbers, because this set would not be closed under like additional multiplication. Oh, it is actually closed under multiplication. But it doesn't, but it only works here because of like special properties of these norms for like these p-adic fields. And this ZP will be like closed under additional multiplication, and it will like act as a ring of integer, just like how Z acts as a ring of integer of Q. And like, so one property in particular is that the QP will be a field of fractions of ZP. And in fact, you can obtain QP just by inverting P. So like once you adjoin P inverse to ZP, then you will get QP. But this is besides the point. So this ring of integers is also in Leen. So now rather than, so this is an important philosophy in when we use Leen, is that in mathematics, we always say the something. Like, for example, we will say the ring of integers of QP is ZP, and we will also say like the algebraic closure if you're not careful enough. Like some people already say an algebraic closure, but some people still say the algebraic closure. And the point is that these objects are like not unique. Like even though they are all like isomorphic, like if you have another copy of ZP, like as in like if you have another definition of ZP, then it will always be isomorphic to this thing, but then they are not the same objects. So like this is a bit like problematic if you want to work with like different models of ZP. Like for example, what if you made ZP first and then you define QP to be the ring of to be the field of fractions of ZP? In that case, like ZP will not be equal to this set because this set will be like a subtype of QP, but this ZP will be like an independent type of its own right. So what do we do in this case is that we introduce this very important concept in Leen, which is called the characteristic predicate. So this characteristic predicate is like rather than specifying one object, we specify what it means to be a ring of integers. So in this case, R, let's say if you have this QP is R here, and then O will be this ZP. What it means for like O to be a ring of integers of R is that we have an inclusion map from O to R. So they're represented by this injective line. So this is injective because it's a subset, but it doesn't need, here it is a subset, but in general, when we consider isomorphic things, it doesn't need to be a subset, but it will still have this map. And this is just saying that the image of the map will be this subset. So it's just saying that everything here, like everything in the image has norm at most one, and then everything that has norm at most one is in the image. So this might seem like trivial. This is you are just stating this differently, but this is somehow very important because this allows us to like unify different models of objects that we build. This is also used in like localization. So this is I'm referring to like localizations of a ring. So initially, like maybe when we first defined localization, it was defined as like one particular ring. Given a ring and a multiplicative set, then we constructed this sort of like localization as a ring, as a fixed ring, and then this is somehow problematic as we try to use it in the theory of schemes, because there we need to localize twice, and then there are like two ways to localize twice. Like you can do it one step at a time, or you can like do it all together by combining the two sets, combining the two multiplicative sets, and then just localizing it all together. But the problem is that these two different approaches gives you different objects, because they are like, even though they are isomorphic, they are not the same object. So somehow all this became a mess when we tried to define a scheme in Leen. So what happened afterwards is that someone came along and said that localization should not be a fixed object. It should be a predicate. We should characterize what it means for a ring to be a localization of another ring given a multiplicative set, and then and then they got along, and they just defined this whole predicate, and then everything became better. So this characteristic predicate is like very important in the theory of when we use lean. So what next is the tilting. So what do we do to tilt this k we just defined? Is we call that we define k to be the completion of QP adjoining all the p to the nth roots of p. So the tilting will be called k flat. The flat is the tilting, and how we make it is by taking k and then using this map sending x to the p. We take the inverse limits over like this map, which means like we form a tower of k, each mapping to the next by like this map, and then we take the inverse limit. More concretely, we define it to be like the set of sequences indexed by natural numbers, such that each one is a pth root of the previous one. So you can see here that the n+1 element to the power p is the nth element. So this is how we concretely define construct this perfection, this tilting. Here we call it perfection. But this only makes sense multiplicatively, because like categorically speaking, this map does not preserve addition. This map only preserves multiplication. So the inverse limit we only agree like multiplicatively. And we recall that this doesn't preserve addition because we are not in characteristic P. We are in mixed characteristic. If this were in characteristic P, then this would be preserving addition. But actually, if we like work over if this were characteristic P, then this would be an isomorphism because of our assumptions about our local fields that we can tilt. And this will be, so what this means is that once you tilt it, you will get a field of characteristic P, and then if you tilt it again, it will do nothing. Because if you like have a field of characteristic P here, and this map is an isomorphism, then the inverse limit will just be isomorphic to the original thing. So this tilting is an idempotent functor. So here monoid means like structures preserving multiplication. Like monoid is the analog of ring, but like without addition. Since like in lean we define things in like maximum generality, even though our theorems might not apply to those maximum generalities. This is why we define it for like monoids, even though Schulze would not have considered tilting a monoid. So this is like another philosophy of lean, is to define things in maximum generality, because definition is like different in lean and then in math. Like in maths, definition is like just like something, doesn't matter. But in lean, definition is like contains data, and like it's also used like in notation. So like for example, when we have division in lean, as like many of you would have noticed, when like the first time you use lean, you type division, and then lean doesn't ask you to prove that the denominator is non-zero every time you type division. Like in contrast, like in mathematics, we consider it to be undefined when the denominator is zero. Every time we write the division symbol, we are making sure to ourselves that the denominator is like not zero, right? So, but in lean, that we can't sort of carry all these proofs around, because it would be very troublesome, and it would make the notations like very, very long. So like we strive to define things with like maximal generality, and then in the theorems we introduce like gradually the assumptions. So this is why we define, like this is why in here I define this perfection for monoids. Later I also define it for like characteristic P rings. But this is not important now. The important thing is that, so this tilting is formed like this multiplicatively. So I haven't specified the addition. So the addition is like given by a formula. So if you recall that these things can be represented by sequences of like pth roots, like choices of pth roots, then the addition formula looks like this. So this is sequence xn, this is the sequence yn, and then if I add them together, I obtain a new sequence defined like this. And you can check that each one is still a pth root of the previous one, because you just take this to the power p, this will end up with being k plus 1, and then the index shift, and then everything works out, and then yeah. So this just works. This is the addition formula. There's also like another way to obtain tilting without this formula, but there's like more convoluted like stuff. So in this presentation, I will only like introduce this formula. So, and then you can check that this formula works for like adding multiple stuff together. So if I have three things like x, n, y, and z n, then I can modify this formula by having x, y, z here, and then the formula will still work. And in particular, if I have p copies of 1, so what is 1 here? 1 is represented by the sequence of constant ones, which works because 1 is a pth root of 1. So if like, imagine I have p copies of 1 here, so what would this be? So this inside will be p, because I'm just adding p copies of 1 together. So this is p, and then this power is p to the k. Like as k tends to infinity, this p to the k also tends to infinity. And then if you remember what I specified about the p-adic norm is that p to the n gets closer and closer to 0 as you increase n. So since this p to the k like goes to infinity, p to the k will go to 0. So this limit is always 0. So this sequence is just constant 0. What this means is that if I add p copies of 1 together, I get 0. And this is why the tilt has characteristic p. And so so this proves that tilting is gives you a tilting a mixed characteristic field gives you a field of characteristic p. So this is a basic example. Another properties about tilting is this projection. Since if you remember, I defined the tilt to be like concretely, I defined the tilt to be like sequences of pth roots. So I can just project to the 0th coordinate, and you can, so this map will preserve multiplication, and then addition will be, this map doesn't preserve addition, but you can sort of see what it will become using this addition formula. This map is also denoted sharp as the opposite of flat, although they are like not strictly opposites. Like they are somehow related, but like it's not a strict inverse of this flat thing, which doesn't even make any sense, because this is flat is not a function, right? This flat, I'm not. There is no function flat like from like k to k flat. This flat is a functor, and then this sharp is somehow sort of inverting somehow. This is so, and then this is basic example. Like if so, the k and k flat are what's Schulze called perfectoid fields because of some assumptions of the norm and some other assumptions on the field. So Schulze defined this whole functor on like perfectoid fields, and like fields of mixed characteristic will be sent to fields of characteristic P, and then you can also define like sort of similar things for varieties, and this is how Schultz proved his theorem. Yeah, and yeah. So this is the end of the presentation. So if you have any questions, please feel free to ask me.
Can you hear me?
Yes, I can hear you.
Are you done?
Yeah, I'm done.
Right, I will stop recording.